Welcome to this presentation where we continue to talk about content contained in the book Introduction to Nonlinear Control. In this presentation we are going to talk about content contained in Chapter 3, namely linear systems and linearization. While this book focuses mainly on nonlinear control techniques and nonlinear systems, it is extremely valuable to have some background knowledge on linear systems to be able to extend these methods to nonlinear systems, or the other way around, to linearize nonlinear dynamical systems and then draw conclusions for linear systems and use them for the analysis of nonlinear systems. So that's why before diving into the next chapters on nonlinear control directly, we go through a couple of concepts discussed in linear system theory. Okay, and a general potentially nonlinear system is described here through x dot is equal to f of x, f being a function from n to n. A specific system of this form could be expressed as x dot is equal to a times x, where now f of x is just this matrix multiplication here, and in this case we have a linear time invariant system. So the linear time invariant system is a special case of the general time invariant nonlinear system. Why is it useful to study linear systems in particular? Well, for linear systems we know explicitly the solution of the dynamical system, namely it's simply the matrix exponential times t times the initial condition. So a solution is given through this expression here. Additionally, what we've looked at in the previous talk was equilibria and properties of equilibria. For linear systems, the origin is always in equilibrium. And if we want to study stability properties of a linear system, that means we only need to look at the eigenvalues of the matrix A, because stability properties of the origin are completely determined by the eigenvalues of A. Additionally, we know that local stability properties are equivalent to global stability properties, and asymptotic stability is equivalent to exponential stability. So these are special cases that hold for linear systems, which are not necessarily true in the context of nonlinear systems. And well, stability, instability, and exponential or asymptotic stability, as mentioned over here, is completely determined through the eigenvalues of A, because we can state the following theorem here, which essentially says that if all eigenvalues of A have negative real parts, then the system is exponentially or asymptotically stable, or not the system, the origin. If there is an eigenvalue which has positive real part, then the system is unstable. And if we are in the case that we have eigenvalues with real part on the y-axis, on the imaginary axis, then we have to be a bit careful, and it could either mean instability or simply stability. As a last point, for nonlinear systems, we looked at Lyapunov functions to characterize stability properties of equilibria, because an eigenvalue theorem was not available to us. For linear systems, we can also define Lyapunov functions, and there are specific Lyapunov functions, namely quadratic Lyapunov functions of this form, which exist if and only if the system is asymptotically or exponentially stable. So existence means there exists a positive matrix P here in this context. And we can also state a corresponding theorem here. So again, looking at the linear system x dot is equal to ax, then the following are equivalent, namely the origin is exponentially stable. That is equivalent to all eigenvalues having strictly negative real parts. So that was also stated over here. Or as a third equivalence, if we look at this Lyapunov equation here and take an arbitrary positive definite matrix Q, then we know that this has a unique solution P, a unique positive definite solution which satisfies this equation, which provides us a corresponding Lyapunov function. So, yeah, in the context of nonlinear systems, it's a lot more complicated to verify asymptotic stability, exponential stability, instability in general, and to find Lyapunov functions. For linear systems, it is a lot easier, and there are explicit methods that tell us how to verify or check stability. How do these results help us in the context now of nonlinear differential equations? So getting back to our original definition, x dot is equal to f of x. Now making the simplified assumption that we have an equilibrium at the origin, and for the following results we are going to need that a function f is continuously differentiable. What we can do in this case is take the linearization, so take the derivative of f with respect to x and evaluate that at 0 and define that as our matrix A. And then we can define the linearization of our nonlinear dynamical system at the point x equal to 0 through this linear system here. So to differentiate between nonlinear and linear system, we use a different variable. So instead of x, we use z, but now we end up with a linear system z dot is equal to a times z as an approximation of the nonlinear system. And in this case, the following theorem can be stated. Namely, if we consider our nonlinear system, here under the assumption f continuously differentiable, and if we then look at the corresponding linearization, z dot is equal to az, then the following relationship between the stability of the linear system and the nonlinear system holds. Namely, if the origin ze equal to 0 is a globally exponentially stable equilibrium for the linear system, then this implies that x being equal to 0 is a locally exponentially stable equilibrium for the nonlinear dynamical system. So we've seen on the previous slide that for a linear system, local stability properties are also global. Here we can draw a local conclusion that exponential stability is preserved if we linearize our system. Or vice versa, we can use the linear system to verify if our nonlinear system is exponentially stable. The origin is exponentially stable. Okay, so to summarize that, yes, the local exponential stability properties are preserved under linearization. And that means that in many cases, the linear approximation of a nonlinear system can be used to draw conclusions about properties of the nonlinear system. But that's not always the case, so that needs to be kept in mind. So sometimes it works. Perfect, then we can use methods from linear control theory for nonlinear control theory, but sometimes that's not possible, and then we need specific nonlinear control methods. So when is it not the case? So there is a simple example which you can look at as an exercise. Consider x dot is equal to minus x to the power 3. Now, using Lyapunov methods, you can show that the origin of this nonlinear system is asymptotically stable, but it's actually not exponentially stable. But if we look at the linearization, then we end up with x dot is equal to 0, because the matrix A in this case is 0. If we look at another example, x dot is equal to x to the power 3, well, then it can be shown, again, using Lyapunov theory and corresponding Lyapunov methods, that the origin in this case is unstable. But if we again look at the linearization, we end up again with x dot is equal to 0. And yeah, in this case, we have the difference here that we start with the same, or we start with these system dynamics, two nonlinear systems. We can show using, we can show that the origin of these nonlinear systems in one case is asymptotically stable, and in the other case is unstable. So in one case asymptotically stable, in the other case unstable. But then if we look at the linearization, we end up with the same linearization for both systems, and implying that the linear corresponding system is actually stable, but we can't draw a conclusion for the nonlinear system. Okay, this was for systems without inputs. We can also look at systems with inputs and with systems with output, and extend the linearization method from the previous slides to systems of this form over here, where we also already have seen extensions of equilibria, namely that here in this context we can look at pairs of equilibria with a state and a corresponding input. And through a coordinate transformation, we've also seen that we can shift the equilibrium pair to the origin and can assume that without loss of generality. In this case, the linearization means that we are going to obtain four matrices. Namely, we first take the derivative of f with respect to our state x, then evaluate this expression in 0, 0, our equilibrium pair. This provides us a matrix A. If we differentiate with f with respect to u, and again evaluate it at 0, 0, and then we can denote that with the matrix B. And similar, we can linearize the output equation, first differentiating with x and then with respect to u, giving us this, these two matrix pairs AB and CD, which then define a linear system with input and output simply defined by these four matrices. And yeah, if we have now these four matrices, then we don't even need the notation over here. Instead, we can simply use this notation ABCD to unambiguously define a linear system. AB simply describes the system without output, and AC describes the output behavior without input. So these are standard notations, these matrix pairs. D is often not present, so that's the direct feed-through term. What is then usually studied in linear control courses is controllability and observability, a property again captured in the matrix pairs AB or AC. Controllability means the ability to go from an arbitrary state to an arbitrary state by selecting the appropriate input. Observability means, are we able to reconstruct the state X based on output measurements Y? Another thing that's usually done in linear control theory is controller design, stabilizing the origin. And this can simply be done through pole placement, for example. So what one would look at, if one has a controllable or stabilizable system, then one would try to find a controller gain K to be able to define a feedback law U is equal to Kx, such that the corresponding closed loop system described through this new matrix A plus BK now has an asymptotically stable origin. So what we can see here is that in many cases, if we are only interested in a local analysis of our nonlinear dynamical system, then it is sufficient to look at the linearization and under certain conditions, properties of the nonlinear system are preserved in the linear approximation. Meaning it is sometimes sufficient, and then we should use that information through linear systems to just look at the linear approximation. However, if we want to enlarge the domain of interest, or if we are interested in global results, then we need potentially more complicated methods directly applicable to nonlinear dynamics. And that's what we are going to focus on in the next chapters. So yeah, that concludes the brief overview or recap of linear systems. And then we continue in the next video with a brief overview of frequency domain analysis, which predominantly also is on linear systems, before then we then continue with the next topic.